work that we're, why this work, even though it's really sort of fundamental physics work in the fire environment, why this is somewhat relevant to your work now, to managers' work now, and why it's probably going to be more relevant in the future. And so really this is sort of about giving sort of the nuts and bolts of sort of the state-of-the-art of fire science research, at least within the realm of the physical fire environment, quantifying it and modeling it. So and another thing that this is sort of for is we have, this seems really big, and so our ability to sort of communicate is kind of diminished a little bit as a unit. And so as this project has been progressing, we sort of noticed that, hey, well, I didn't know you were doing that, or what are you doing? And so we had sort of come to this idea to have sort of a webinar series internally as well, so that we could share what we were doing and share new ideas and make sure that we're collaborating together. And so I thought it would be just a good thing for sort of everybody to participate in and to sort of see how, what we're up to. And so our group gets to see that, and sort of so do the rest of you. So that's sort of the leader's intent on this, I guess I would say, is to sort of like give a glimpse. And so just sort of as a background of this project, and these slides delay a little bit, so please just stick with me. I'm trying to anticipate that delay while I'm talking, but there's a little bit of delay from what's on my screen and what you guys are seeing. So I think we've got that figured out. So this sort of big project, and it's sort of the genesis of the project was a RFP, or request for proposals, from the DoD actually, and they are interested in developing a better understanding of combustion processes. So they basically went through sort of a large process of looking at sort of every year they look at different things that are implements to training, implements to other things that they're doing, and then they try to focus and dig down into those things and to solve those problems. And that was sort of the genesis of this solicitation. And so we applied, and the call really, and you can look at just the bold, you don't look it up, look at all those words, but they're interested in sort of fine fuel heat exchange, ignition, fire spread, and fuel condition. And so really just this sort of the physical dynamics of fire, how fires interact, how heat is transferred, what different sort of meteorological parameters mean to fire spread, and also sort of the fuel condition, the arrangement of the fuels, the type of the fuels, all of those sort of things in a nutshell. And so though the goal of this RFP wasn't to build a new model or build any models really, but the idea is that this research supports new models, and that these models will be developed in the future, hopefully with follow-on funding in the next couple of years. So I'm going to buzz through these real fast, but they had sort of 4 research needs that they identified. This open combustion processes at different scales. You'll see scale talked about a lot here. How fire spreads across heterogeneous fuels, so different fuel beds, different fuel arrangement within sort of the similar fuel types, those kind of sort of really kind of fine scale nitty-gritty questions about how fuel affects fire spread and behavior or fire dynamics, and then also the role of those characteristics in these combustion processes, how that affects combustion, and then also looking more at this sort of coupled fire atmospheric dynamics. So how are fires interacting with sort of the greater atmosphere, even at the near field and also far field. So they're really broad questions, and there's a lot within each of those. And so a lot of the proposals that were submitted sort of really tried to dig down into one of these. And because we're overachievers and ambitious, I think that we've kind of tried to attack all 4 of these with our project. Okay, and so if we look also, and I don't think I really talked about it, but this was all supposed to be focused on sort of low intensity fires. They weren't interested in looking at crowning fire behavior. They weren't interested in looking at sort of like really like a running wildfire. That wasn't the focus here. This was low intensity fire, and when we think about that, that's sort of the fire that, when I think about it, it's the fire that we use, right? It's prescribed fire. On a wildland fire, it's also maybe a burnout operation. That could be a lower intensity fire. So the frame of this really for me is a better understanding of the fire that we use. And so I'm lagging here already, I can tell, but sort of like a sort of low intensity backing fire is sort of what we had originally come up with, especially many of us coming from the Pine Barrens. There's really not any low intensity fire other than a backing fire. So our initial focus was to think about looking at these backing type fires. So it also matters to us that because when we think about models, and the models are really being pushed and are being utilized as a primary sort of guide for what kind of management operations we're doing, why we're doing what we're doing, in the context of wildland fires, where is the fire going to spread to, what are the values at risk, trying to find those kind of things. And most of these models were developed under the context of wildland fire suppression. They weren't developed looking at sort of low intensity backing fires, like I said, the fire we use, or burnout operations, those kind of fires. I mean, these models are basically designed to look at sort of the worst case scenario, and that's how it's been attacked. And so this is just sort of an example of the scale that some of these fires or some of these models are being worked at. So this is a photo of the Rough Fire map from a couple years ago that Gallagher and I spent some time on. But basically, the far side runs for this are at such large scale. And, when we're doing sort of managed fires, we're not talking about a 28,000 acre prescribed fire. Many times we're talking about a 100 acre or 200 acre fire. So some of those larger constraints have been sort of washed over in these other models. And it also matters to us, and why this is sort of an important thing, is that many of the models that have been developed or are sort of son and daughter models based on models that were developed long ago. And Farsight is based on the Rothermel model, which was developed in 1972. And I don't know if you guys have looked around at all, but man, technology's really changed. And so a lot of these models were, developed empirically, looking at very simplistic spread and parameterized using rather simplistic experiments. And frankly, we're sort of in a better place now with our capacity to measure in the field, so to quantify fire behavior, to quantify fuels, and also then to computationally understand what that data means to us. So we're sort of in a much different world now technologically, but we're still using these sort of older, more mature models. So that's sort of the impetus for what we're doing. And I just really kind of briefly want to sort of differentiate between different ideas or types of models. This will be helpful as all of these go forward. But when we think of Farsight or we think of the Rothermel model, that's an empirical model. And so it was based on measurements and observations. Okay, that's the definition of empirical, is based on observation. So they lit a fire and then they measured every step of the way. So my fire and this fuel went, 10 chains per half hour or per hour or something like that. And then they upped the wind a little bit. Now it went 20 chains in that same time period and things like that. They collected those data and then they developed this empirical model based off of those. And so there's really not any sort of physics in there. It's just sort of, we have observed this behavior and we're able to, build some kind of regression model that then predicts, we're able to predict that outcome in the future. And so those models are really good in some cases, where you have a homogeneous fuel bed, or you have a really, you've done a lot of experiments in, say, like oak hickory forests, and you've really, just beat your head against the wall measuring all these things and building a model. And the problem is that they don't really transfer outside of that realm. So where we have a lot of these experiments, that data is good, but if we try to take that same model and apply it to something that isn't the same as we collected the data, then it starts to fall apart. And unfortunately, a lot of these models have really been pushed outside of the realm of where they really belong. So the difference is, and I'm not going to explain this very well. Eric and Mike Kiefer can explain this down the road to you guys. But the difference is that with sort of physics-based models, is that we are able to, we're trying to represent the fundamental physical properties, and we're trying to sort of nail those things down. What's the difference between radiative transfer and convective transfer? Those kind of questions, and to actually understand those physics and then apply them in the computational environment to develop a model. And because they're physically based, they should be able to transfer a lot more easily. Now, the issue with these is understanding the physics, first of all, and then just sort of the raw computational power that is needed to model, a needle burning next to another needle, and why is that igniting, and then what scale can we work at, and where can we find efficiencies? These are not operational. They're just not there yet, and they might not ever be. But we can use them as a tool to sort of understand what we don't know. So I'm not going to really get too far down to the nitty-gritty of this. And like I said, we sort of have taken on a bunch of different tasks within this project. And, as this webinar series moves forward, each of these tasks will have at least one sort of webinar tied to it. And we'll go back over that list a little bit later. But we will talk about, we're very interested in looking at physical processes in multiple scales. We're really interested in how do we better quantify fuel beds, and also how do these multi-scale atmospheric dynamics fit into what we're trying to do. And so those are really broad objectives, and these were written out objectives, and I just sort of bulleted them for you guys. But we have sort of sub-investigations going on in sort of all of these realms. So like I said before, these low-intensity fires are important because they're a management tool. This comes back to why are we doing this. And they're also, when you are doing some fire suppression, if you have a flank and a wind shift, that low-intensity fire turns into a problem rather quickly. This is just a sort of brief example, and this is where we're going to really start to fade away with the timing of things. But if you watch this GIF that I have up here, it should come up in a minute if it hasn't come up for you guys yet. This was an experimental fire that we had lit probably 7 or 8 years ago. It was a prescribed fire, and we were blacklining this fire. And we it's probably, you can't really see the block here, but you can see where the torchman is going up. But anyway, we probably had about a half a mile of black line backing fire lit. And, we had this really nicely behaving low intensity fire, and while the wind shifted, and now we had a half mile of a running head fire. And so we ended up burning, in about 4 minutes what we had burned out probably in about 2 hours prior to that. And so this is one of those cases where it is important to understand these lower intensity fires. And they're difficult for us to model. And one of the reasons why is that we have all of these physical processes going on, and they're happening at multiple scales. And in a lot of cases, they're happening at scales that are sort of smaller than the model is able to handle. So we call that sort of subgrid cell size. An example of that, I have two examples here, and I'll try to play them, but I don't think it's really going to work out too well. But on the top frame here, we have a head fire, and you can actually see some really cool fire whirls going in there. Maybe it's, I know, sort of stop motion animation for you guys, but where that head hit the road, and we had some channeling effect. And so there's all these processes that are going on at sort of this larger scale in that top fire. And then we also have sort of the same processes happening at a much different scale in this bottom fire. And it's pretty tough to resolve, what do we need to know about those processes at sort of this head fire scale, and what's different about them, and what will transfer and what won't transfer. And so understanding those two different things are very difficult. There's a lot of different things that are probably influencing the bottom fire that aren't influencing the top fire at all. The rate of spread of that top fire is probably ember-driven and direct flame bathing. The bottom fire, I mean, the rate of spread of that backing fire, is really probably dependent on some kind of really small-scale eddying that's pushing the flame against the wind for a second or two. You can see it's sort of flickering in there. So differentiating and understanding and finding efficiencies between those two is really important. Another reason why fires can be difficult to model is that we have these really crazy fuel bed characteristics, and you have heterogeneity across the fuel beds. I mean, sort of the solution in the modeling realm, or in the management realm anyway, is to have these sort of fuel models, Scott and Berg and 40, those kind of things. But as we step away from some of these empirical models and start to get to the physics-based models, it now sort of matters sort of where all of the foliage is. A Scott and Bergen model tells you, over this sort of grid cell size, you have X amount of fuels, and that's here, and it doesn't really talk very much about the distribution of those fuels. These physics-based models need that kind of information because we're looking at very complicated wind fields through that system. We're looking at drag. How does that oak in the middle, how does that deform with the wind to alter the drag characteristics of the fire environment? So very sort of small scale things that are really having a large scale impact on the fire behavior. And we're trying to capture that. And then we also have these sort of different scales of atmospheric science that need to be addressed, right? A fire like this was about 4 minutes after this fire was lit. It was a single linear ignition, and you can really see how this fire is very dependent on what is going on in the upper atmosphere above it. It sort of jumped out of the gate. At other times, the atmosphere is different, and those dynamics are changing at much different scales. So understanding that also is a large part of this project. So we have all these things that we're trying to look at, and to get down to sort of how are we going to solve these, or how are we going to try to. We have quite a research team. We have, I think, 7 different universities that are working on this project, and the Forest Service folks as well, from all over the world. And so we work in a very collaborative environment. There's a lot of very specialized people on this list, and we're all sort of working together towards these sort of end goals. And we have sort of this conceptual framework of how we want to have this project be sort of iterative. So basically, we sort of have been starting in the middle with this sort of idea of this numerical modeling idea, right? We're basically trying to build better models, even though we're not really trying to build better models. We're trying to collect data to help us build better models. So the modeling is basically the center of what we're trying to do. And then around that, you can see these other sort of experimental scales that we're working at. So we're doing a lot of small-scale bench testing at the University of Edinburgh, also some table work. We're doing some mid-scale lab experiments at Worcester Polytech. And so, again, we're taking these same fuel beds, the same fuel types, and looking at them at these very, very different scales. And we're also doing some small-scale field experiments, 10-meter by 10-meter things that we can get a lot of reps out of. And then we're also incorporating a couple of observational burns, and those are sort of our ground truth for a lot of the fire behavior work, but they're also where a lot of those atmospheric processes are actually going to take place. So we don't really have enough going on in a lot of the other areas that we're able to look at much atmospheric perturbation. So one of these, the first thing we'll talk about is this modeling idea. And this is the way we're using the models is, at least to start with, is to basically do a sensitivity analysis where we are able to identify different variables within the model and look and see how they affect the outcome of a given model run. And we're using that to really target the different variables that we're looking at within the other experimental realms. So in this case, you can see that this model, everything was sort of held constant except for 1 or 2 of these things were tweaked through the model. And you can see that this variable in particular came out and had a large impact on the performance of the model, or at least not even the performance, but there was a lot of variability between the model runs. So this is something that we would focus on in the lab. One of the mechanisms that we're using in the small-scale laboratory experiments is sort of a table burn. And so this table is pretty cool because you can see here that we have these sort of pivot tubes that are actually within the fuel bed. So we're basically burning over the top of them so that we can look at the flow dynamics as the fire is burning over the top of those tubes. And so we can look at different things like different fuel loads. How does that flow dynamic change? We could also look at different bulk densities. So the same fuel load but trampled or rolled or something like that, and look and see how those things affect what's going on. So we'll try these two. Try to let you guys catch up for a second here. So this is just sort of an example of one of those table burns on the left and an infrared monitoring that we're doing on the right of the same burn as well. And so a lot of these same concepts we're bringing through each of the scales. So we use the same instruments as we scale up. And so we can look even at something as simple as the height of the sidewall on here and how that's affecting what we're actually measuring on that lab bench. And this is sort of part of the analytical portion of just sort of testing the bed. And then we sort of come back to our numerical modeling, and we can look and see how well does WFDS, one of the computational fluid dynamics models, how well does that capture what we're seeing when we're actually doing the burn on the table? You know, are we able to look at is the mass loss the same? Are the other fire dynamics the same that we're able to measure, and sort of tie those back together? And so look, basically we perform the experiment and then we look at the model. Does the model agree with what we're getting? Do we have relatively good agreement? If not, what's the problem? That's sort of the iterative nature of what we're doing. So we then go back to the lab and try to solve that other piece of the pie that we're not understanding quite yet. So moving from the small scale, we're also doing this sort of in the larger scale, and this allows us to work with, you know, larger fuel particles or shrubs, things like that. And so we designed a wind tunnel that's housed at Worcester Polytech that allows us to burn inside of the wind tunnel. And within that tunnel, we're able to make some very, very high spatial, we have a high spatial resolution of measurements that we're able to make very accurately to quantify basically what the flow is. So if we put a needle bed in there and we run a fire through, what is the flow there? And then also then if we put one shrub in there, how is that changing the turbulent environment? How is the drag from that shrub affecting how the fire is spreading in there? And so we're able to really control that in the hood at WPI. And this thing's actually kind of novel because it was designed to go outside as well. So this wind tunnel is designed to be plopped down on a field plot in the woods, and so we can basically use a natural fuel bed and make the same kind of measurements while controlling the wind in the field. So basically and that's another sort of truthing kind of thing. So do our lab measurements line up with what we're seeing in the field? And we figured that the best way for us to do that was to actually take the tunnel out into the woods. So that's probably going to be coming on at some point next year. Excuse me. Okay, moving from that scale, that sort of lab-based scale, we want to now eventually move into the field. And so we have a setup. It's really kind of a concert setup. I mean, we've been using concert trusses as the vehicle for holding, or the apparatus for holding all of our instruments. And so we're trying to get a lot of repetitions of a 10 by 10 burn and really just sort of instrumenting the snot out of it. So in our design here over that 10 by 10 space, we have 16 anemometers. And then there's sort of these profiles of thermocouples in the fire as well. You know, we have 8 sort of thermocouple profiles going. We have an overhead infrared camera that's capturing the fire at about 4 centimeter resolution as it moves through the plot as well. And so we're able to really look at how the turbulent environment in this plot is changing, and what's different from A to B, or, you know, things like that. We've actually started to do some manipulations also where we're basically doubling the fuel or tripling the fuel in these burns, and then even doubling and then compacting with a roller. Those actually, we're going to be working on those next week. So how do we sort of measure all these variables that we're trying to get at, and really what resolution do those measurements need to be taken in? And so this is sort of a neat little way that we've been igniting these, so we get a single linear ignition all at the same time. And I don't know, you guys are lagging probably a little bit, but that gives a really good picture of what the setup looks like also. So each of the sonic anemometers in this video are logging at 10 hertz, so 10 times per second, 3-dimensional wind speed and temperature. We also have a sonic anemometer on the tower that's in the center of this plot, and it's logging at the same rate right next to the infrared camera. And so we're able to look at this sort of the horizontal spatial variability of the wind field within that plot. And again, back to the iterative nature, next time we do these burns, we're actually going to have the sonics up and down on top of each other. So we'll be looking at the vertical heterogeneity also. And so it's like a data explosion. Shindy Bien did some, from the Forest Service, did some preliminary analysis on these data. But we basically, each one of these graph figures on the left, we have for each one of those sonics for each one of our burns. So data management is a large issue in this project as well. So that's sort of how we're measuring the fire environment during the fire, but we're also doing a lot of fuels quantification in these plots as well. And so we're really looking at sort of three-dimensional fuel structure, sort of down to the needle bed as well. And these are just sort of examples of, these are terrestrial laser scans of one of those 10 by 10 plots. So A is sort of the precondition, B is the raw scan, C is the scan as it's been segmented into individual trees, and D and E illustrate how we're able to separate the trees from the ground. And so if you look really hard at E, you can sort of see our little fire lines in there. So very high resolution LiDAR data. There's a couple million points that are taken for each plot. So we're doing this before and after, so because we're trying to get a consumption. And so we think that with the resolution of the TLS that we're using, that we're going to be able to look at combustion across the plot at very high resolutions, even on the needles. So this figure, and we've been scanning these with our instruments in them also, so we have a really good spatial idea of where our instruments are. But this is showing basically the green is the post-fire and the red is the pre-fire. So you can see the difference, especially on the forest floor. It's really defined on the left-hand side of this, but you can sort of see what the mass loss was of that needle layer. And this will come. So we also, I should have mentioned this before, we sort of started with the easy case, which is just sort of pine needles in a plantation. But as we move forward in our work here, we're going to be introducing sort of shrubs with leaves and shrubs without leaves as we burn. And so we have a really big challenge ahead of us for the physical quantification of those shrubs, the structural quantification of those shrubs. And this figure is just an illustration of some work that we've done in the lab looking at building three-dimensional models of the shrubs using an engineering LiDAR that we use to scan each of these things. And so we basically come up with a three-dimensional model of individual shrub components. So this is sort of very preliminary work. But as we move into the realm of shrubs, we're going to have a lot harder time. And then this is sort of just some of the infrared camera. This is before the burn. So I put this in here just to sort of demonstrate. We're at the top of a tower looking down on our setup, so you can sort of see the trusses in the frame there. So the dark blue are the actual trusses, and they're still cold. It's early in the morning, but then if you look in the plot, you can actually see these light blue trusses as well. And so that's formed from the shadow of the truss. You can see the shadow of each of the stems in there as well. And so this is just sort of an illustration of how highly variable the fuel temperature can be, even in a fuel bed that is really just a flat, it's just flat land with needles on it. And we still have this much temperature variability. And try to imagine what you then have if you had a shrub layer and some kind of understory layer, and what the variability of this fuel temperature would be in that case as well. So we're also going to be moving to these small-scale field experiments into the same realm of modeling that we did for the lab work as well. So we're trying to model these things too. Does the model match up with what we see? If not, why not? Let's go back and fix it. That's really kind of the whole idea of what we're doing here. And then we also have these large-scale field experiments, and basically they're prescribed burns, these large-scale experiments. We're not specifying anything. These are operational burns. And so it's a real challenge for our team to properly instrument a large-scale burn. We've been putting all that equipment in these little 10 by 10 plots, and we can do 3 of those a day. We can move all that equipment 3 times a day with the right amount of help. But then taking that same set of equipment and basically scattering it across 100 acres is a much different kind of challenge. And so one of the other things that we're doing, and Bob Cremens is going to actually specifically talk about this, is sort of the state-of-the-art of instrumentation and what we're able to do. And so this is an example of something that Eric Mueller came up with from Edinburgh, but it's basically the same idea of the pressure probes here on the left-hand side that you saw underneath of the fuel bed in the lab at Edinburgh in the table experiment. So basically trying to get that same kind of measurement out in the woods somewhere It proves very difficult though, and the scale that we're measuring at it's really hard to tell if we're capturing the scale that the fire is behaving at. This is another example of some sort of really fancy field sensors. This is a network that Eric built also of thermocouples, and each one of these things on the left is one data logger, one thermocouple, and it has a GPS in it as well. And you can fit 5 of them in the palm of your hand. And so basically, Eric has been running out and burying all these and GPSing them. And then as we burn through them, and this is the same fire actually that I showed you the picture of the plume for, as we burn through those, we're able to get the position of the fire. And I hope you can see the fire sort of sweeping through here on the right-hand side. If you watch it, right where my pointer is, which you can actually see a spot fire out ahead of the head fire. And that's not anything that we've ever been able to really get at before. And this is a very small, probably 200 meter by 200 meter fire. But it's really kind of neat to look at those dynamics, then to go back at the fuels and the weather and to see, well, why do we think that this actually behaved the way that it did? And the final part of this is the sort of atmospheric dynamics that we sort of touched on briefly. And this plume, again, it's my favorite picture right now. But really looking at how do these sort of atmospheric models do when we're looking at these larger scale phenomenon across the landscape or looking at an operational burn. And these are slices through ARPS, which is an atmospheric model, looking at basically what the wind speed is above the ground. These are simulated. What the wind speed is, distance from the fire. So the fire is actually in the center of these graphs at 0. And you can see like this TKE thing, that's kinetic energy. So basically a measurement of turbulence. And you can see how turbulent the fire is there. And so it's really challenging for us to come up with the proper field measurements to actually go ahead and, I don't want to say validate, but validate these models, really. I mean, how do you do that kind of thing? How do we know that we're getting good results from the models? And that's what a large component of those operational burns that we're going to be doing comes to. So with that, I just want to, that's just sort of meant as a very general overview of all of the things that we're doing. I mean, I barely touched on anything. And if any of those things sort of struck your fancy or you're interested in the future, these are sort of simplified title talks for everybody. But Mike is going to be talking about the three-dimensional LiDAR data that we've been collecting and how we're using that to really parameterize fuel models coming up next. And all the way down through so that essentially each of those parts has a very specific webinar tied to it as well, so we can sort of dig down into that. I want to acknowledge the funding for this project. I wouldn't say that much funding for this project specifically came out of the Joint Fire Science Program, but the Joint Fire Science Program in previous funding is really responsible for linking together that huge team that you saw. We all work together through JFSP grants, and this work is really just sort of follow-on of a lot of the work that we did with that, and also the DoD SERDP program that is funding us now and hopefully will continue to fund us for the next 3 years as we move on with this project. And also, you know, doing this, and everybody pretty much knows me on the phone, but I will tell you again and again that this does not happen without good partnerships with land managers. And, you know, that's what this slide is really just about, thanking those folks for really sticking with us through all this stuff. And a lot of times we do things that are very applied. You know, it makes sense. This is why we're doing it. And a lot of this is maybe applied in about 10 years, you know, so it's been a challenge, and they've really stuck with us through that, even though they're not really seeing a direct benefit right away. So that's what I got. And these are the upcoming webinars with their proper titles.
All right. Great. Thank you so much, Nick. That was awesome. A really excellent overview of a lot of really deep topics. Again, for folks on the line, we will have the real videos posted on the NAFC website soon, but it actually looks pretty decent, being able to see some of the fire in motion and getting the sense of where it was coming from and how it progressed and how that related to the measurements. We had a question that came in so far in the chat box. Oh, two questions. So keep on adding those questions to the chat box. The first question is from Allie Reiner. And Allie says, for the type of modeling you are all delving into, will you relate the LiDAR point clouds to fuel loadings and biomass, or somehow use LiDAR data directly in fire modeling?
Yeah, Ali, that's a good question. So there's sort of two. I think that with LiDAR does a couple things really well, and different types of LiDAR do different kinds of things well. I think that earlier in my career, I think that I was really kind of focused on using LiDAR as almost like a statistical tool and looking at, so you have a LiDAR point cloud, and within that point cloud, you have all of these sort of variables that you can sort of extract, right? So what's the mean height or what's the maximum height, those kind of things. And then you can use those and relate them to fuels data that you're collecting, like canopy bulk density or biomass. Biomass is the easy one because we have FIA plots to really understand. Or you can just go do a plot and relate to whatever you want, whatever field variable you're collecting, you could then use some LiDAR variables to then model, using some kind of regression model. And so using that statistical approach, you can get it like fuel load, canopy fuel load, things like that. I think that works really well for sort of empirical models or at larger scales, those kind of things. If we're looking at like landscapes, if we want to model fire in the landscape, that's a sort of a very useful way to use LiDAR data. Or if we want to look at the effectiveness of a fuel treatment, we can do that with looking at that bulk density or at biomass or whatever variable you pick. And what we're doing now, and there was another sort of call, and one of them was really to look at three-dimensional fuel structure. And I think that we're kind of moving in a different direction with the CFD modeling, where we need to know the physical shape of the tree. We basically need a model of like every huckleberry that's out there. Like if there's 50 huckleberries, like I want to have like a wireframe mesh of those 50 huckleberries. Or if there's a bunch of stems, like I want to have a wireframe mesh of those stems, because we want to understand how those are affecting the turbulent environment within the plot. And so it's a very different kind of thing that we're looking at. So when we talk about combustion with LiDAR, I think that we're using that sort of statistical approach. But at the same time now, we're actually getting into this sort of, it's called quantitative surface modeling, where we're trying to use point clouds to build models of trees and shrubs. So I hope that answers the question. So there's sort of two different sort of realms of LiDAR work.
Got it. Thanks. We had a comment that came in. John Cecil says, "Nice job, Nick. Awesome to see the detail showing how the burn progressed." And I would definitely agree with that. It's really cool to see this in motion and being able to see it quantified. We have a comment also from Tim Simmons, or actually a question. Tim's asking, will there be any quantification of fuels that have been mechanically manipulated?
No, I don't think so, Tim. Probably not in the way that you're thinking. We are going to manipulate the fuels, but it's going to be they're almost going to be stylized, if that makes any sense. Even in a wind tunnel, it's hard to recreate nature sometimes or to understand that. So in the wind tunnel, we've been using these sort of stylized dowels to start with to look at sort of how does the fire spread from one dowel to the next dowel to the next dowel. And I think that we're trying to get that really I don't want to say easy. We're trying to get that basic stuff down before we would move into like a manipulation treatment, or even I would even say before we move into the real world, we're trying to get sort of the basic stuff down so we can understand it. So within the context of this now, but we will be manipulating the fuel bed, so we'll be adding fuels and things like that. But in some cases, we might actually be cutting trees out or shrubs out because it's too much. We've actually talked about this is one of Gallagher's ideas, and he's full of them. But we've talked about basically taking our wind sensor setup out. And because it's kind of interesting just to look at the flow within the canopy, even without a fire. We don't really understand that very well, let alone put a heat source in there and see what happens. But basically putting our sonic anemometer setup out there and basically starting from zero with no trees or just overstory trees, and then basically adding pitch pine trees that are like on posts, like little shrubby trees, and basically building a forest within that and looking to see how the winds change in that scenario. So stylized, but probably not really necessarily real world all the time.
And again, the goal is to sort of understand the physics behind the fire, and you're not quite at the stage of applying that to real world, but that will be coming soon.
It will hopefully be coming. I won't say soon.
All right. Cool. Again, folks, please type questions into the chat box. and we'll see if we definitely have time to address a few more questions before the top of the hour. Let's see. In the meantime, Nick, do you have any afterthoughts? I know you were trying to, hurry through and cover everything. Did you have any other kind of postscripts that you wanted to add onto what you presented?
Not really. I had one. There was one thing. I would say that one of the other things that with these empirical models, what the difference is, there's really no output from it, right? And like they're just basically, you're just trying to model the fire, and there's not really like, you're not getting like a heat flux off of it or anything like that, so you can't really use them to look at like fire effects. So one of the sort of potential things, and I really think that the physics models are probably just a tool for now for scientists, but in the future, you're going to be able to model like heat fluxes into like a tree, so you will be able to look at like stem mortality, things like that, using those models. And you're also you have a much better chance of getting at like sort of smoke dispersion, particulate dispersion, those kind of things, because those physics are actually built into the model. And so it really allows you to look not just at the spread of the fire, but also the model, or other outputs that you're interested in too.
Cool. We had a comment from Matt Duvenek. He says, "Nice job, Nick. Nice to see your progression as a fire scientist and fire modeler, since I was more involved with what you were up to." So thanks for that comment, Matt.
Yeah, no more backpack lasers, Matt.
All right. We'll give folks another minute or two to type questions in. I know there's a lot of information, and people are probably still digesting everything. But just again, as a reminder, the webinar series is listed on the North Atlantic Fire Science Exchange website. If you go to our homepage and click on the fine scale, big scale icon, then you'll see all the latest information, and we'll be able to get into greater detail on all this great research that's going on in the upcoming webinars. So if you have more detailed questions, you'll be able to talk with some of the scientists that are working on it right now. All right. I don't see any additional questions. Oh, yep, there's one more. Okay, Allie has another question. From your perspective, how many years until physics-based models will be available for operational use by fire managers to manage large-scale fires in complex fuels and terrain? Great question. Good luck, Nick.
Well, Eric Mueller's talk is on. You have to ask Eric that or Ruddy that. I mean, so I'm just sort of the paperwork guy on this stuff now, and I kind of guide the LiDAR work. But I would say that one of the modelers would probably tell you that they're far off from that being the case, but they're not far off from informing sort of semi-empirical models. So where we can use these physics-based models almost experimentally to come up with, to figure things out, and then apply those to sort of new semi-empirical models, or just sort of retrofitting older models, but using the knowledge that we're gaining, using these experimentally or sort of in a research capacity to move forward. But I think it's going to be a long time before, I don't know. I wouldn't say within 10 years, I mean, maybe in some really rare cases, but I really just see them as a tool. One of the things that's really cool, Rod Lynn and Kevin Hires and those folks are using FireTech to look at like sort of different like management scenarios. So FireTech's another one of these CFD models that was developed at Los Alamos. And they're looking at sort of like interacting fires. So how does a fire behave if you have a bunch of ping pong balls that you drop from a helicopter and then the wind shifts or something like that? And then they're trying to actually sort of line it up like with manager experience. Like, does that make sense? And so that's the kind of sort of almost like gaming, I think, that is going to come out of these before they're ever going to really be operational. I don't know, though. If you think about just the technology over the last couple of years, how things have changed, it's phenomenal. There's like the cost of a terrestrial LiDAR has gone, a good one has gone from over $150,000. Now there's one on the market for $15,000. And, just even photogrammetry with drones or, different things. It's just crazy. So I would say that the validation of the models is a real problem right now. I think that there has not been enough sort of field work that has been completed to really kind of get a good picture of how these things are working or why they're working or why they're not working. I mean, we can make pretty pictures and have awesome sort of visualizations of things, but it's the whole garbage in, garbage out thing, and at some point it becomes science fiction. And so sort of field studies like this, and this isn't the only one, there's 3 or 4 of these that were funded across the country doing sort of similar things, looking at those other tasks. But these are the kind of experiments that are needed to see that we're not creating science fiction. And that's the thing. So I think it's going to be a while. You knew that.
Still a good question. So Warren Haldeman chimed in. That is correct, Nick. And then Ken Clark added, one of the great benefits of research efforts like this is that all the data are archived for use by others, not just us. Very nice talk, Nick. And Ellie said, just asking, thanks. It is a good question, though. But yeah, and the archive data, I mean, so much that has been recorded at Titusville Little Experimental Forest, you're rediscovering now and reusing. And if you think about the original fuel models, empirical models from the 60s, that was 50, 60 years ago. So can you imagine where we'll be 50 or 60 years from now? So 10 years. We'll have a follow-up webinar in 10 years and see how close you are in your estimate. But I think there's a lot of great research going on that will hopefully help inform management. And definitely, you've got your work cut out for you. Are there any final questions in the chat box? I don't see any at the moment. We'll give people just maybe another minute. Any final comments, thank yous you want to share? All right. So we're 5 minutes till 1 by my watch. I think we are good to go on this webinar. Thanks everybody so much for joining us, and we hope to see you. These webinars are every 2 weeks. And again, check the NAFC website for the latest information. Thanks everyone for joining us, and great job, Nick.
Thanks, guys.